So continuing on the wind and solar lecture videos, we have finished off in this slide previously, and so I'm gonna restart on this slide. And so we're talking about challenges and solutions. So looking forward to the future. So I already talked about sensors before. The other problem with wind power is, in this case, how well we actually integrate the energy created from wind power to our actual energy grid. So that has been a very problematic solution. One of the things is obviously when you convert it into batteries, like when you convert the energy and you store it into batteries, that's actually direct current. And obviously you need to, in this case, then switch from direct current to alternating current in order for it to be integrated into the grid. So that's actually a very big problem. All right, so that's another important thing. The other thing obviously is if you actually have in this case, if you don't create enough power or enough current, then what you need to do is you need to have a step-up transformer, obviously. But one of the other big things is obviously the type of batteries. If we are going to store power in a wind turbine, especially if it's for household use, we know that the limitation of the wind turbine is dependent upon how efficient in this case, our actually batteries are in actually storing energy, right? So no matter how much energy we actually can create with a wind turbine, what happens then in this case is we actually cannot store all of the energy in a battery. The other thing is variability, obviously. So variability means to say that there are days in which we have we have wind speeds that actually can actually transform the mechanical energy into, in this case, electrical energy in a battery or into the grid. The other thing is there are days in which we actually have none whatsoever, right? So one of the things that has been proposed to solve all of these things is obviously to store the energy that we have from the actual wind power for future use. So when days in which we have no wind, then we can use that stored obviously power into a usable form. So there's been a lot of proposals. So I'm going to be talking about pumping water between reservoirs at different elevations soon. But one of the things that you can actually do, and they've been talking about this, is you could actually use the wind power to actually, in this case, pump air, right, into basically you're just trying to pressurize air. That's basically all you're doing in this case. So what happens is when you pressurize air, eventually you can store it in a container or a cavern. And what happens then is that compressed air then, right, when you need energy, then can be released, and that pressure, right, being released from that compressed air can then, in this case, generate power. So that's one way. The other way that you could do this is obviously you can actually use wind power to split water to create hydrogen, right, hydrogen gas. And then obviously hydrogen gas is highly combustible. So what happens is when hydrogen and oxygen combines, you create water. And that reaction actually creates a high amount of energy. And so you can use then, in this case, hydrogen as a form of energy. All right. So now talking about different elevations, this is actually what they've been doing in Spain. So what happens is you actually have, you have to understand that there's actually a lot, on this case, here's the wind farm here. So what happens during windy days, right, in which there are, in this case, conditions conducive to the creation of wind power, what happens is this wind turbines then obviously store energy still into batteries, or still probably in this case, actually in Spain, it's highly mature technology now, either the power that's generated from the wind then in this case is stored in batteries, or actually in this case integrated into a grid. So obviously that's fine. But in days in which you have excess energy, in which the grid like does not need any more support from you, or in this case your batteries are saturated with power, what happens is the leftover energy, the excess energy, is used to pump water from a lower reservoir to a higher reservoir. So this is in a lower, in this case elevation, this is in higher elevation. So the excess energy after the energy from here is stored in batteries and into the grid is used to pump water up, right? In days in which there are no viable wind to actually turn this wind turbines, what actually happens then is the water that's now in an elevated thing is actually then, there's actually a little bit of a dam here, and what happens then is you can then release the water that was stored from a higher elevation, and the flow of water from a higher area to a lower area, similar to a dam, then creates, in this case, turns a turbine, and that turbine then creates electricity in this case. So this is one way that you can actually store excess energy during surpluses of wind power. Okay, and this is obviously in Spain. I don't know if we're doing this in this country. Okay, so that was wind energy. Now we're going to be talking about solar energy. Switching to a new topic here. So solar energy, FYI, comes from the sun. Obviously, that's why it's called solar. And that the reason why we get so much energy from the sun is because actually there is actually a reaction that actually occurs involving hydrogen gas. So the actual sun is actually in this case actually has less and less and less and less of hydrogen gas, and so the combustion, in this case the reaction that involves hydrogen gas, is what's creating this solar energy. FYI, I think that there's a few more billions of years, I think, that we actually have before the hydrogen gas that actually is actually fueling this reaction eventually runs out. At that point, obviously the sun is going to, like in this case, first of all glow, in this case create this expansive energy that which will basically kill basically almost life on the planet, and then eventually it cools down, it blows up. Okay, and then life on the solar system, well, life on the earth as we know it, because this is the only place that has living things, will eventually cease to exist. Okay, but I digress. So the energy from the sun, okay, is actually quite incredible. So as you can see there, there's this calculation. The other statistic that I would like to tell you is the energy from the sun in 1 second hitting the Earth's surface is enough to give us power at our current electrical and energy needs for a few hundreds of thousands of years. So just think about that for a second, right? 1 second of solar energy, obviously we're talking about all of the surfaces of the earth here that is being hit by the sun, right, is enough to power our current energy needs for a few hundred thousands of years. Some people actually say almost up to 500,000 years. So the problem, of course, is the energy from the sun is so small, right? And it's very diffuse. So what it means to say is it's actually in this high vast area that we need to concentrate this. Okay, so this is actually the disadvantage here. And obviously it doesn't shine consistently if we have like cloud cover. Okay, so energy, like when we have weather patterns that actually prevent like the sun to actually hit the surface of the earth. Okay, so this is addressed by, in this case, it says collection, conversion, and storage, and obviously this is where solar panels come into play, because that's actually how you collect the energy from the sun, you convert it into electrical energy, obviously, and then you store it in batteries, or obviously you can actually also like put the actual solar panel grid into the grid. Right, so that's actually how you could actually get energy from the sun. We've been doing this already because we've actually been using solar energy to actually heat our water in some instances in some households. Okay, and we actually use already like solar energy if you have plants inside your house, right? Or if during sunny days, this is one of the reasons why sunny days in the winter time you don't have to heat your house as much. Okay, so that's actually one of the ways that we've been applying this. So, but my main concern now, although you are still responsible for the great bulk, okay, of all the 30 PowerPoint slides that is actually in this module, again, this is please be aware that you need to read through all 30 slides. And again, these lecture videos are just a very, very quick summaries of what I consider to be like complex topics. Okay, so the main, okay, like driver of, in this case, of solar energy and photovoltaic cells are actually solar cells. All right, and what solar cells do, all they do in this case is they convert, in this case, solar energy, right, into electrical energy through the movement of electrons, and that electrical energy through the movement of electrons gets converted into current, which creates either, in this case, direct current electricity, or you can actually store that direct current electricity in batteries, or you can transform that direct current and you can actually basically put an inverter in between you and the grid, and what happens is that direct DC electricity and it's converted into alternating current, which is obviously what goes through our power lines, right? So how do solar cells work? So this is a very, very complicated topic, and I'm hoping that I'm going to cover it in the next 5 minutes. All right. But before we even talk about that, I need to talk to you about doping first. Okay, no, doping is not when you actually take dope. All right, doping is a term that we actually talk about when we talk about like impurities. So the main in this case, the main component of solar cells, primarily speaking, first generation solar cells, is actually silicon. Okay, silicon is an element. Silicon is actually similarly to carbon. What happens is silicon is actually connected to 4 other silicon. It's actually, so you actually have one silicon connected to 4 other silicon metals. Okay. The problem with silicon is we actually call it a semiconductor because it can conduct, or it can insulate electricity in this case, right? And what happens is, however, with silicon is when it's connected to 4 other silicon, is there are no free electrons around to actually carry around energy in this case, all right, or to actually create electricity in this case, right? So the way that photovoltaic cells work is what we call doping. So we have a P junction and an N junction, basically talking about positive and negative junctions. And positive junctions are doped with boron, another type of element, and the negative junction is actually doped with phosphorus, which is another type of element. All right. The key here between P and N and positive and N portions of a photovoltaic cell is boron actually has an electron hole. So it actually has space where electrons can actually occupy. In phosphorus, we actually have free electrons. And I'm gonna like designate electrons by an X, okay? Right, so phosphorus on one end actually has an electron that is free to move around, and boron on the other hand actually has space in which electrons can actually occupy. So that's actually the basis of P and N, right, portions of an actual photovoltaic cell, positive and negative portions. Now, the reason why this is called a negative portion is because if there's an excess of electrons are negatively charged. So if you have an excess of electrons which are negatively charged, you become negatively charged. And when you obviously have a hole, right, in which case you actually have a gap in which there's no electrons, well, obviously the lack of electrons makes you positive. So that's the whole basis of this thing, right? And again, boron and phosphorus is what we dope substances, in this case, the photovoltaic cells, depending on a P or an N junction. Boron and phosphorus is only a small component of both of these areas. The majority of this component is still silicon. All right, so it's silicon in this side with just some phosphorus. It's a lot of silicon on this side with just a few boron atoms. That's all this is. Okay, so what happens obviously is, since you have electrons on this side and since you have holes on this side, electrons will always travel from an area of greater concentration to a lower concentration. It's called diffusion. So what happens is they're going to flow from the N side to the P side, right? I hope that makes sense. However, as you can see here, there's this area here which is positively charged, and the reason why this is obviously if you lose electrons, if electrons are going from this area to this area, what happens to the area in which electrons have vacated? Since electrons are negatively charged, the area in which electrons left behind will now become positively charged because they have left. The area in which they have traveled to, in which they've filled holes, is now what we call negatively charged, because guess what? Electrons are negatively charged. So basically the take home here is electrons are negative. When electrons go to an area, that area becomes more negative. When electrons leave an area, that area becomes more positive. Okay, I am going to pause this video and I'm going to continue on with this solar cells working in the next lecture video.